Sorry. How's that? You're looking so good.
It's very nice.
Yeah,
Very nice.
yeah, okay.
All right, guys, let's go ahead and get started with lecture 8 this morning. It's going to be a relatively quick one, I think. Part 2 is scattering. We mostly focus on scattering measurements, instrumentation around scattering, just a few examples of scattering in the environment, and maybe a little inspiration at the end. We'll see. Working?
I might just check if it's recording. Sorry, guys. That's recording. Okay. Now I need to double check.
No worries. All right, again, Meg's roadmap figure, just kind of where we're at. It's Thursday. This is part 2 of scattering. After this, you'll have a lecture on particle size distribution as well, getting more into the details of how that's calculated and some of the fun aspects of that. Today's lab will be scattering and beam attenuation measurements. So we'll take water samples and move them around the lab and measure it with several different instruments. So just reviewing yesterday, scattering is excitation plus re-emission. So that electromagnetic plane wave hits charged particles. All those charged particles within the charged elements within the particle re-emit secondary waves, and we get the result of scattering. For small particles, they're much more isotropic, like that. The larger particles get, the more near forward you scatter. We define the volume scattering function. It tells us everything that we need to know about unpolarized radiance or unpolarized scattering in the ocean. And then we looked a little bit at the polarized case where those, like pretty much everything becomes vectors and matrices. From the VSF, we calculate the scattering coefficient. Backscattering is really important for remote sensing applications. And then did some other IOP connections with scattering. So we plotted a lot of VSFs yesterday, looked at phase functions. I used the Petzold phase functions and VSFs as an example. And we kind of pointed out two things there. Across all water types, there's roughly 2 orders of magnitude, 2 to 3 orders of magnitude of variability in just the strength of scattering. And within any one scattering function, so as a function of angle, there's 6+ orders of magnitude in variability. So that's a big instrumentation challenge because you've got to have a sensor that can cover 8+ orders of magnitude of dynamic range. Beyond that, you've got sort of the most obvious way to think about measuring the volume scattering function is to build an instrument where you have a source shining a beam into the sample volume, and you've got some sort of receiver that's looking at the beam, and you're able to rotate it around some central scattering volume. If you're positioned out here, you're looking at the near forward, right? So the light's coming this way, and you're looking at the forward part of the light. Similarly, you can rotate yourself back here, and you're looking towards the backwards angle. So in terms of the definition of VSF, we kind of designed this receiver so that it's measuring an intensity. So there's a solid angle aspect. So this has a finite width that it's looking at with the beam. And just a couple of quick notes on this one. So one thing you can see immediately is you can only move like this receiver so close to the source before you start, before you run into the source. So that limits your backwards angle range. And if you start looking at VSF data from real instruments, you'll see that there's generally only so far they can go towards the backwards directions. It takes a very specialized instrument to measure very, very close to the back, towards pi. And similarly, you can only get so close to the forward beam before you're starting to block the beam with your receiver. So there's a lot of different measurement challenges here. So there's that geometry aspect. There's also a lot of design trade-offs in trying to manage that dynamic range. What sort of angular resolution do you need? How long do you need to integrate it at these positions? How long does it take to do a full scan because of that integration? So there's a whole world of pain, suffering, and joy from building VSF instruments. Now, one approach to do the near forward is the list. So this is an instrument that Sequoia Scientific makes. The basic principle of the instrument is that you've got some sort of source. So we use a laser. We have a reference sensor where we can actually measure the strength of the source. That goes through a collimating lens and through a transmit window into your sample volume. So this is the newer version of the list instrument. You'll play with an older one today, get a little longer path length. But you've got two windows and a sample volume where water can get into. So that beam goes through the sample volume, goes through another receive window here, and then there's what's called a Fourier focusing lens. And then there's a ring detector at the focal length of this lens. So, and then through on the other side of this ring detector, there's a pinhole in the middle of the ring detector and a laser power detector. So without even thinking scattering, this is a transmissometer, as Emmanuel showed yesterday. You've got the amount of power going into the sample volume, and you're measuring the amount of power that makes it through the sample volume. So that gives you an immediate transmission measurement. So this kind of zooms on the sample volume and looks at what happens with scattering from the sample volume. So this focusing lens has the property that scattering at any position in the sample volume at a given angle, let's call it psi 1, will hit this ring detector at the same radius. It's just a property of a Fourier transform lens. It's the Fourier transform property of a lens, rather, that will measure scattering at some radius for any angle that scatters out of here. So that gives us essentially the near forward VSF. The instrument is used by design at Sequoia for measuring particle size distribution, because as we showed yesterday, diffraction, the shape of scattering in the near forward depends strongly on particle size. So there are mathematical games you can play to invert that data to get particle size distribution. But today you'll see it used as a volume scattering function sensor. So another way to measure more general angle scattering is, rather than move that arm with the receiver around your sample volume, position a number of detectors around that beam. So this is the mascot instrument. This was designed by Mike Trudowski, well, Jim Sullivan, when they were at Wet Labs, which became part of Seabird. This was never commercialized. It's a research grade instrument, but it's pretty amazing, because one really interesting aspect about this is, because you're not dealing with moving a receiver around a sample volume, you're able to interrogate your volume scattering function very fast. You can see the beam from all those angles at the same time. So you can resolve dynamic events like those surf zone images I showed, or phase functions I showed yesterday, where you had wave suspension, sediment suspension. You can see the effects of bubbles come and go. Mike often would deploy the sensor with a list to get the near forward. So this actually sees from 10 degrees to 170 degrees with a detector at every 10 degrees. And the detectors are very well characterized. And then you add a list that gives you from about 0.01 degree to 10 to 15 degrees in the near forward. So if you combine those two, you can get a merged VSF that covers from very, very far in the near forward to 170 degrees. So this is just an example of profiles from in Santa Barbara. You can again see that very strong near forward scattering. One other quick note: he also has done work where he puts a polarization system in the beam so that he can look at the degree of linear polarization.
Going back to that previous plot, is there like an offset between the mascot?
Yep, you can see it.
And what is the
just differences in calibration between the two instruments. Like if you're going to merge two instruments or two size distributions, you've kind of got two choices. You can calibrate each one absolutely as best you can, or you can merge them. And I believe his approach here is that he would calibrate each one very, very well independently, but at times you would still see a slight mismatch in some of the volume scattering functions. You can see right there. So kind of have to make a choice. I'll go over, we actually make that choice somewhat in the list VSF instrument. Have to make a choice there. This is the list VSF. So this is another way of looking at scattering at multiple angles. So this is looking, it uses a little bit different approach. Rather than swing your arm around the sample volume, what this does is use, there's transmit optics that send a beam into the sample volume. So your sample volume is open here to the ambient flow. And so looking at the beam, you've got this eyeball here that's rotating around this axis. So looking down at that axis, you're actually scanning the beam. And as you're scanning the beam, you're changing the angle with which you're looking at the beam. So you're changing your scattering angle. So this is just another way to get the volume scattering function. Additional steps you have to process in order to deal with sort of the geometry there. But it gives you a really nice, one nice aspect of it is that you have the same detector looking at the beam. So you're calibrating one detector. What we do here also is have sort of the standard list optics. So there's the ring detector and all that stuff here. And so you're getting the near forward, and then the eyeball is looking at the larger angle. So you have to merge those two, same idea. In our case, we don't calibrate the eyeball, we calibrate the ring detectors and then merge the two together. This is just some examples of looking at size fractionated sediment particles, Arizona dust. In the list VSF, different size ranges have different scattering functions. And you can kind of see if you look, they're sloped a little bit differently corresponding to the size. This instrument, similarly to the other, like in looking at that swing arm aspect, we only see out to about 150, 160 degrees, just because then we start to actually look at the pressure housing. So let's say we can measure the VSF, right? So maybe we don't always need the full VSF. All of those instruments are pretty expensive or not commercially available. And there's many cases where we really just want the backscattering, because we can relate that to different biogeochemical parameters, remote sensing. So if we look at full VSFs, beta here, and then normalize it to backscattering, we get a pretty consistent shape. So we call this the backscattering phase function, or backscattering function. And what you see here is there's kind of a place where there's very little variability. And if we think about it a little bit, this is both the wide range of Fournier-Ferrand phase functions, and then the data with error bars is a very large data set of those mascot VSFs. And so this is a pretty wide range of conditions, and there's an area where there's very little variability. That suggests that we could actually use measurements of VSF at a specific angle to estimate backscattering coefficient. So instead of measuring the full VSF and trying to integrate it, we could just measure it at one angle and then just empirically connect the two. It's really powerful because that's what pretty much all volume scattering function measurements with ecopucks or hydroscats or MCOMs or SC6s, all of these different sensors use this principle. So we can rewrite this plot, we can design an equation around this where we say the backscattering is equal to the volume scattering function times some coefficient chi, which varies as a function of angle. That just is a way of expressing this average curve. And there's some angle psi where the variability is minimal, and we would probably design our backscattering instrument to measure volume scattering function. These are two examples of backscattering instruments that are out there. So there's up top some Seabird eco scattering sensors. These are what you'll see on gliders. They're very common in our field. They have typically a single angle you'll see today maybe one that has 3 angles in the backscattering direction. All your FLNTUs, BB3s are this sort of instrument. And then you'll also see a Sequoia Hyper BB today, which is similar to the hydroscat in the way its optics are designed, but again, it's a single wavelength. These measure at 1, maybe 3 angles, 9 if you have a BB9, but that's just 3 of these stuck together. This measures from about 430 nanometers to 700 nanometers at arbitrary steps. Typically, we go about every 10 nanometers. You'll use this in the lab today. You'll use both in the lab today. If we think about our swing arm, we're still measuring volume scattering function by having essentially a beam going out from the instrument, and then our detector is put all the way in the backwards direction. Most of these instruments aren't super well collimated, so they actually look something like where they've got diverging beams and a wide field of view. Hyper BB is fairly collimated, but there's a consequence to that, to that spread. Oh, it's not on there. So looking at how that chi factor, if we're going to make a sensor that's going to measure backscattering from volume scattering function at a single angle, we're going to need to know what that factor is. So there's been a lot of work in the last decade or so in nailing down that chi factor. There was a lot of sort of controversy, confusion, lack of understanding, partly because we didn't have the volume scattering function measurements to be able to calculate chi. So this is some recent work by Xiaodong Zhang, looking at MBSM, which is another volume scattering instrument we saw some data from yesterday, and the LIST VSF from the field. This, I think, was Ocean Station Papa. And he gets really good consistent agreement between the MBSM and the LIST VSF. And then he also looks at that chi factor from pretty much every study that was available in the literature, and that's on the right. You can see it's reasonably well constrained in there, but there's some areas where we have a lot more confidence in the number. So in that, 120, 130, 140 range, we get a lot more confidence than if we were to try to build a sensor to measure backscattering by putting the detector at 160 degrees. There's not much agreement between environments and methods. So, like I said, with these sensors where you've got the wider field of view, wider beams, there's a consequence to that. And that's that rather than measuring beta at a single angle, you're measuring beta across a range of angles, right? So if you've got light coming into your sample volume, even if it's pretty widely spread here. This is a hydroscat, cartoon of a hydroscat. You're going to get light into your detector from a wide range of scattering angles. Similarly, this is the Eco VSF, so this is a little bit different optical design, but you've got these LEDs here, and if we just look at this LED, it's got a pretty wide emission. But then if you look at the field of view of the detector right here, that's the blue lines, it's very wide. So you're getting scattering from a lot of different angles are going to make it back into this detector. So we express that by just looking at take the ideal VSF, and we come up with this weighting function W. And what we're actually measuring with the instrument is this average beta at some centroid angle, call it the centroid or nominal angle, and just effectively weights the response that we're to let us understand that we're not measuring at an ideal specific single angle. So there's 2 ways we can determine this weighting function, because we need that in order to do measurements and further data processing with these instruments. We could do it experimentally by taking a known reflector and actually moving that reflector as a function of distance away from the face and measuring the response from that reflector. So that actually lets us sort of map the sample volume with the actual light that's going out and the light that's coming back in. So it's a sort of absolute calibration of the system. And then the other way is numerically by sort of making assumptions about the geometry, that you have a certain spread of light being emitted, a certain field of view of your detector, and then you just numerically essentially make a virtual version of that calibration plaque that you move away from the instrument, and you numerically figure out what should make it back to the instrument. And so those are the two real ways of measuring the weighting function and sort of the approaches to calibration. The big sort of papers there, Mafione and Dana in 1997 on the hydroscat, describes the math of that actual plaque calibration, which is sort of intense. And then numerically, Sullivan et al. in 2013, and then recently Zhao Dong and Emmanuel and some folks did another look at that. And that's numerically pretty intense as well. So this is what those look like. So rather than dive into the math of the plaque calibration, we do have the plaque calibration set up for the hydroscat. If anybody wants to look at that as a project, we have that. So you're welcome to play with that. If we want to think about the numerical side of it, because that's actually kind of nice in thinking about different aspects of the sensor, because we can change things numerically in our model. Look at how it changes the weighting function more easily than we might do it in an experiment. So this is from that Sullivan paper. And you can see here, we've got our source emitting its light, detector seeing light coming from a certain range. And literally, he just makes grids of numbers moving away from the sensor and figures out where there's overlap between the two and assumes that light makes it back. So just to generate a weighting function. These are two approaches from the Zhang paper, looking at the similar idea. Again, the weighting function, this is now mapped in terms of angle. So he's kind of showing which angles are making it back into the sensor. And this is for two instruments. One's the hydroscat, so you can use the virtual plaque method with either sensors, with any sensor that you know the geometry of, and then for the EcoBB. So one of the important things to keep in mind here is when you use the real plaque, physical plaque, it's an absolute calibration of the system. You have the actual light going out of the instrument, and you're measuring the actual light coming back into the system. So you can take that and get actual physical units of per meter per steradian from the instrument based on the physics and the known traceability of that standard. If we calculate the weighting function numerically, there's still another step we'll have to go through to connect the weighted response of the instrument to the physical units of, say, per meter per steradian of volume scattering function. And we'll typically do that by putting the instrument, looking at its weighted response, and comparing it to a known standard like calibration microspheres, so little beads that we can show you in the lab today. But the size distribution is really well known, and then we can use that to connect the digital numbers coming out of the instrument to the actual physical quantity that we're interested in. Yes.
So this angle is based on the construction of the instrument that's not actually validated. You also assume that your source is an homogeneous emission. And if you ever look at an LED, you see that there's not parts. They're not necessarily but the assumption is the calculation is not on the level. So you're not, these are things that you assume are correct without checking.
Yeah.
But when you do the plaque method, it's taken into consideration that all these things, all these issues that are taken into account.
Yeah, you get it sort of empirically. It's built into the calibration. It's absolute. There's one thing that you don't necessarily know, and that's the reflectivity of the plaque. But you know that pretty well. These are the type of like reflectance standards that they use for calibration of satellites and really intense stuff. Yeah. But you at least only have one uncertain parameter there in the plaque calibration. So it's one, versus it's well constrained versus the bead approach where you've got uncertainty in your index of refraction of the beads and the size of distribution of the beads. And the big uncertainty is the assumptions you make about the geometry of the instrument to get those weighting functions. I didn't show it here, but so over the history of using these sensors, there's been several sort of iterations of what those weighting functions should be, and even what the angles of these instruments are. If you look at eco literature for the last 10 or 15 years, you'll see a range of sort of nominal scattering angles that are reported, 117, 124, all these different things, because it was sort of assumed based on modeling the instrument. And as the models improved for the instrument, we figured out, oh, actually it's a wider size or a wider weighting function at a different angle. And there's a really interesting plot, either Jim Sullivan or Twardowski put together, where they plotted those over sort of history. And you can see the very first ones for the eco-VSF were these triangles, where they made fairly crude assumptions about the geometry of the instrument. And then more recently, by doing this full model here, or at least, the next level of that model, it smooths out, it's in a different spot. Kind of interesting. Did somebody have a?
I was just wondering, sort of what you talked about, how they choose the scattering angle, especially thinking about that minimized at 115 degrees.
Mhm.
Why is the eco compound maybe at 140?
There's engineering constraints too. That's you could measure it probably at either from an engineering standpoint. It may have been that they designed those optics when we thought it was at a different location. I honestly don't know. I mean, the Hyper BB we designed around 135-ish. That was partly just because David Dano and I worked on the instrument, and he designed the hydroscats around the same angle. The nice thing is out here, unless you're way off base, it's still pretty well constrained. Like, there's enough assumptions in the measurement here that you still know it within 10% ish. Do you have anything to add on that, Emmanuel? I mean, as far as the choice of angle?
Look how wide.
Yeah.
Look how wide the eco side are compared to the other side.
Yeah.
So anybody who's using the VSF in the right direction will affect an eco BB like that. So now you might say, well, I need to do what I want. You have to be a little bit consider when you calculate, because these don't be able to like anything like this.
Yeah.
And so it is something to be aware of, and just so you know, people who calibrate not necessarily take into account the food availability. So particularly as far as I know, the nominal rate, but the angle will be 120 and the nominal or the pool also weighted in each method. About 29 a month. And that also affects.
And they vary unit to unit.
Right?
Typically varying unit to unit as well.
And very unit and very directly to the nominal.
Yeah.
And we talked about it, in fact, we could have 700 months. Actually, 95, 95 radius is 90.
Yeah.
So,
yeah. Yeah, engineering wise, there's a little bit of a trade-off between trying to get a nice collimated source and receiver to give you a weighting function like this versus a wider one. If you look at the sensor, so compare this sort of eco style where you've got an LED that's emitting and a detector with a wide field of view. There's no lens here, I don't believe. Whereas in the hydroscat or the Hyper BB style optics, you've got much more collimation happening on your receiver. So you've limited the field of view of your receiver to be much tighter. And the LED there's still no lens, but it's a little bit narrower emission. So in order to make that happen, in order to make this situation happen, you tend to have the windows a little bit further separated or make the optics way smaller to get them closer together. And so you've got a path length here that's longer than here. So here you're able to get the source and the receiver very close together, which does have some advantages versus a longer path length, but at the expense of now you don't know your central angle very well. All right.
question here.
Oh, yeah. Typically, it's going to be like a single wavelength, but like Emmanuel said, that has some bandwidth to it. So we use a white LED, and we have a special filter very similar to the ACS. It's a linear variable filter that we move through the beam. So we select a 10-ish nanometer bandwidth channel as it's scanning. So it's still a single wavelength coming out of the instrument, but using a filter. Similar to if you put your fingers in the beam on the ACS, you can see it scan through the colors really quick. You can see that on the Hyper BB as well.
And is, yeah, it's about how different ways of gathering or that.
That's hopefully what you get out of the instrument, like how different wavelengths are scattering. Yeah. Yeah.
Yeah, and this kind of is- when you write the calibration paper, they look at the tool.
Yeah.
So each color of that is calibration.
Yeah, we determine like in the Hyper BB, we determine the weighting function at every wavelength channel. So we're as we're moving that plaque away from the instrument, we're scanning all different wavelengths. Yeah. All right, just going to give you a quick overview on things that scatter in the ocean. We touched on a couple yesterday in looking at like the size distribution and how that affects the spectral slope of scattering. But I'll just go through a couple of different examples. Some of you were very excited about the idea of learning about the physics of the scattering of pure seawater. So I'll just give you a couple equations there for fun. Just touch on bubbles, a little bit of turbulence. I think I have maybe one slide on phytoplankton, maybe another on non-algal particles. One comment, I think Meg touched on this, like the idea that what is dissolved? Like what does dissolved versus particulate mean? Ocean optics typically makes the assumption that dissolved material doesn't scatter. But there are particles that make it through the filter, the 0.2 micron filter, that make it dissolved that could scatter. They're colloids. They might have to be in a certain abundance, but if they're there, they could be something that you have to take into account, and that's not typically done. Also aggregates, we're generally assuming solid particles. We're using measurement techniques that disrupt aggregates, so we don't have a good idea on how aggregates, marine snow, things like that affect scattering. So scattering by water is based on this Smoluchowski-Einstein fluctuation theory. The basic idea is your water can be divided into volume elements where you have water molecules moving in and out according to thermodynamics. And this is physics that's fairly above me. But the idea is that as you have molecules moving in and out of that sample volume or that elemental volume, you're changing the density within that volume. And that density is driving fluctuation in the index of refraction in each of those volume elements. So when you're changing index of refraction, that we figured out yesterday, that's scattering, right? That creates scattering when you have that heterogeneity in index of refraction. So that covers the situation of pure water, but seawater has some additional stuff going on because you've got ions. And so this first plot here shows just the idea of your water molecules going in and out of a volume element. So you're changing the density. These blue ions are now the blue circles here are now your ions. So they've got some different density. So you've got a concentration effect where you've got not just the water molecules moving in and out of the volume according to thermodynamics, but also these ions. So that's just an additional way of changing the index of refraction of that volume element. And the third case here is that, let's say our ions are twice as massive as our molecules. We move a certain number of ions in and water molecules in and out. We can keep the density the same, but change the concentration. So there's three elements that come into looking at the fluctuations in that volume. And the state of the art of this up until around 2009 has been to use this amazing data from Morel in the 60s that matched theory very well, matched the Einstein theory. He had, I think, one measurement of salinity that he used to sort of connect what happens when you add salt. And that's been used 60s through, 2009 with just a few modifications as people figure out different parameterizations for the different thermodynamic constants that are in all the equations. And so then if you want the real down and dirty details on the physics, 2021, Zhang and Hu put together a really nice compilation of the seawater properties that sort of summarizes a number of papers that they came out with. And this is an example of their model compared with the data from Morel, and it differs by 2%. I mean, so we're sort of now getting to the point where we finally have a good handle on scattering by water. It is a Rayleigh scatterer, or what we would call a Rayleigh scatterer. Just to give you an idea of what the phase function and the angular variability looks like. Because you'd be disappointed if you didn't see it. These are the physical equations behind it that kind of come out of Zhang. And the reason I wanted to throw this up there is just to show you, out of the physics, you've still got that lambda to the -4. So that really steep lambda to the -4 is something you see pop up with small particle scattering and water scattering. So this is the sort of the basic Einstein's Smol-Yudkowsky theory, where you've got density fluctuation. So, partial derivative of index of refraction relative to density, that's somehow parametered by people measuring it or doing physical models. And then there's your angular variability there. And then when you add salt, you just get these other terms that relate, fluctuations of, for example, the index of refraction relative to the concentration or the salinity. So bubbles. Bubbles are really cool. I showed some phase functions yesterday where there was sort of a baseline phase function from the Scripps pier with lots of resuspension and bubble breaking or wave breaking causing bubbles. And there was a baseline sort of case, an elevated case that had sediment, and then there was a bubble case that had a sort of weird shoulder around 80 degrees. And so this is looking at that data a little bit more digested with those end member cases. So again, the background, higher scattering or higher back scattering from suspended sediment, and then the weird bubble case. And that these shoulders on bubbles come out of the fact that a bubble typically has some has coating around it, typically organic, that acts as a scatterer. So you would simulate these with something like a coated sphere. And then there's a specular component of reflection off the bubble, because you've got basically a mirror here. You've got a water, high index of vacuum or air, and you get scattering specularly. And this is measurements of just bubbles in the lab. And you can see you have that very strong specular component. Turbulence. Kurt's got a very good explanation of the general idea of how turbulence in seawater affects the scattering. And the gist of it is that, again, density fluctuations cause fluctuation in index of refraction. So if you think of density as temperature and salinity changes, you can kind of look at how the index of refraction varies based on fluctuations in temperature and salinity. And what his argument he comes out with is that the change in the index of refraction, the magnitude of the change of the index of refraction is about 10 to the -6, so ppm scale, which is way lower than if you think about when you start to see some of the index of refraction of phytoplankton, which is a few percent. These backscatter or these scattering fractions are pretty low. But the difference is phytoplankton particles, or generally particles in the ocean, are spaced really far apart, so you have a long distance before you have interactions between the light and particles, whereas these density differences in seawater are happening continuously throughout the media. So those changes might be very, very, very small, but they're happening over very large scales, so it's amplified in a sense. So that results in very strong near-forward scattering, very, very fine angles. And this is an example of some measurements of the volume scattering of turbulence. And you can see it's very strong. We were looking at plots yesterday where this is 10 to the 4th, 10 to the 5th. This is, way higher, and we're at angles that are way smaller than we were looking at yesterday. So very, very high forward peaked. Vital, yeah, go for it.
What instrumentation is used to see such small yield?
Check that paper out. It's pretty cool. He basically uses a camera system. So there's, my recollection is he has a plane wave hitting his sample, and then he's got a way of imaging that sample volume onto a CCD, and then that CCD is calibrated to volume scattering function. Using some sort of, I think it was a lenslet array of some sort. Yeah. It's pretty interesting stuff. And just as a comparison, they also did some calculations with mean theory for what they would expect for particle scattering, reasonable assemblages of particles. So it's way, way higher. Just an example. Yeah, it's an interesting paper. It's not too bad to get into. We looked a little bit at the spectral qualities of phytoplankton and non-algal particles yesterday. Just wanted to throw up angular scattering. The black lines here are the Petzold data, and these are some lab measurements from cultures by Bolton et al. In '98. I think Kurt, yeah, this figure is from Mobley. He compiled some of the data from that paper. And you can see it agrees pretty well with sort of the average Petzold shape. Near forward scattering is stronger than back scattering, like you would expect, because phytoplankton are larger than your wavelength. I left that one in there for you, Ivana. Non-algal particles, it could be detritus, could be minerals. I just threw up a couple examples of the scattering as a function of wavelengths from non-algal particles, or minerals rather. And see, there's over here for pure sort of these samples, you've got sort of some interesting structure, and these are measurements. And then you've got some dust samples that were measured by Stransky over here that, you know, seem to have a little less structure, but there's huge variability depending on the type of sediment, or the type of mineral rather. So it's kind of interesting stuff. You know, when you think about, most of your models are going to be just some power law that you're fitting. Okay. No, but that's a good point. I actually put this in here because I wanted to bring up the idea of a specific property. So I think in the biogeochemistry and proxy lectures, you'll maybe see some more of this. But B star is what we would, in this case for minerals, is the mass specific scattering coefficient. So you'll see it has these weird units of meters squared per gram. So what this is if you think about having some, let's say, standard, let's say you're working in an environment where you have tons of calcareous sand. So you know that this is what the shape of that, the spectral shape of that mineral is. But depending on how much of that mineral is in suspension, this is going to move up and down, right? Remember the scattering coefficient in per meter is going to change with the amount of that stuff that's in the water. The shape is because of that, the type of that material. So you would multiply this B star by the mass per volume, the concentration. So mass per volume times this N member of or this mass specific guy here, which is meters squared per gram. Meters squared per gram times grams per cubic meter will give you per meter there. I see. So it's just a way of encompassing the variability of that mineral without worrying about the magnitude. Yes. Yes. Yeah. Yeah. I think it is. What's that? Yeah. Yeah, you'll probably get, so there's another aspect that I think Ivana will probably hit on. I think it's you. So you'll see A star or A phi star, so the phytoplankton specific absorption. And often that could be units of meters squared per gram of chlorophyll, It could be meters squared per cell. It could be meters squared per carbon biomass. There's just, it gets funky. So you always got to pay attention. That's why, again, put units on everything. All right, a couple of quick notes on the backscattering enigma. So we talked a little bit about me modeling, and people have, for the last few decades, tried to figure out how do we model particles in the ocean? How do we figure out how we can explain the biology, the amount of phytoplankton that's in the ocean compared to what we see from an ocean color instrument. And back in the 90s, when people were kicking computers around and doing me theory simulations of what we think the ocean looks like in terms of what's there for particles, a common theme popped up, which is that if we assume that the phytoplankton algae in the water are me scatterers, we could not get enough signal to explain the what we see in the remote sensing sensor, the remote sensing instruments. And so that's typically referred to as the backscattering enigma. And I mean, as contentious as our field gets, other than some other of Emmanuel's opinions about like carbon, or Avana's opinions about carbon too. This was like a pretty big deal. What's that? Oh, Meg, yeah. But it was a lot, there were a lot of hypotheses that were presented for it. Things like, well, there's got to be this pool of colloids that scatter more than we expect, because small particles would explain the backscattering, or shape, or internal complexity of the phytoplankton, or the surface scattering of the phytoplankton. And so even through 2004, in a review where they were sort of trying to look at the idea of colloid scattering, especially being relevant, I just like that quote. I mean, in 2004, we still didn't, controversial. Like when papers are using the word controversial, it's just fun. So more recently, there's been some work in moving beyond the me assumption to explain that enigma. And this is just an example of what that enigma looks like. So here we have a bunch of data that was measured in the surface ocean, places where we expect phytoplankton to dominate. And we have C measured, C modeled, BBP measured, BBP modeled. And to make some assumptions on the size distribution and the index of refraction. And if we find an index of refraction that fits the beam attenuation really well, all of a sudden we're way off on our backscattering. So that me model doesn't explain the data. Similarly, if we find an index of refraction, turns out it's a little bit of a harder particle, n equals 1.11, that matches BBP, now all of a sudden our attenuation doesn't work. So this is like a great one plot summary of that enigma. Like we could not come up with a me model that explains variability. So instead, recently there was some really interesting work modeling, instead of on me scatterers, these relatively simple coded sphere models. We have computer codes that can take a coded sphere model, so multi-layer sphere, where each layer of the sphere is a different index of refraction, and we can model that. And it turns out you can find a very reasonable set of parameters for this that explain both CP and BBP. And the idea is that with just a little bit of extra complexity in our model, we're now accounting for the fact that there's differences of index of refraction within that algal particle. So as the light's going through, it's not just going through and changing phase and interacting with the transmitted wave on the other side. It's bouncing around within the particle, bouncing around within that outer shell, interacting between each other with the two different indexes of refraction. So just a little bit of extra complexity, and all of a sudden now we can explain that data. So that just suggests that the internal complexity of the particle is probably responsible for the enigma. I think there's probably still some dissent, but to me, this is a pretty good indication that hypothesis is valid. And he's on the paper. It was all in the Yeah, but they didn't have to tune the knobs to an unrealistic spot either.
Correct.
It's consistent. I mean, it supports more work in making sure that that's the case.
Maybe it allows to do some modeling.
Yeah.
you know,
Yeah. Yeah, you can now do better models instead of assuming me. Yeah, it's in the right direction. And there's yeah. Yeah.
And now
Yeah.
we distribute it.
Yeah. And if you change your lighting parameters on your microscope, you can see places where you get very strong diffraction around edges, and it varies based on corners. So there's shape effects, there's structure effects, there's other things that support this hypothesis, but this is yeah.
It might, once we have validation measurement, not be found to not.
Right. Yeah.
So, you know, it's.
Yeah.
Or VSF, we do not have.
Right. Yeah, this is with simple BB sensors and transmissometers you'll play with in the lab today. Yeah. But we're still trying to answer questions like this, which is cool. And so this is kind of my inspiration too. Final thoughts. I ripped most of these off from Mobley because I think these are just great. Especially the first one. You guys have played around with the AC instruments now. You're going to play with backscattering instruments. With the ACs, you've got scattering corrections and all these things that you have to worry about, right? You're trying to measure absorption, but you still need scattering. You got to measure both, or you have to at least make assumptions about the other. Similarly, when you're measuring scattering, you're going to need to correct for absorption along the path length as your light goes up to the sample volume and comes back. So the two are coupled, and it's generally not a simple measurement problem of put sensor into the water and measure parameter. You're probably going to need additional information to be able to characterize the measurement you want. So there's a lot of trade-off back there. And then when you add in the idea that often you're measuring both and trying to have closure between those two measurements where you need to correct each other, it gets to be a lot of fun. Let's see. All IOPs are extremely variable, even for something as simple as phytoplankton, right? No single phytoplankton absorption spectra, and scattering, like we just said, we're still trying to figure out how to simply explain phytoplankton scattering. There's huge amounts of variability in that. Models are always approximate. I like this list. These are some good questions to ask yourself when you're picking a model, bio-optical model, or trying to figure out, you know, what spectral slope you should use for your non-algal particle scattering, right? And you find one that came out of a lake in Brazil versus, and you're trying to measure it in the Sargasso Sea. They're trying to model the Sargasso Sea. So, yeah, just ask yourself these questions. This is a good table of check yourself. Yeah. That's it. Yeah, I like it. I think we might have to work with Kurt to come up with a concise list of the laws of Mobley. So he's got great ones like, yeah, I think so.
Any questions for Wayne?
A little confused why